Section 1.3, similar triangles. So in section 1.2, we were talking about congruent triangles. We saw a few different theorems that allowed us to establish that two triangles are congruent based on corresponding sides and angles. And similar triangles, this is just a less stringent relationship between two or more triangles. Okay, so here's the definition. Two triangles are said to be similar if they have equal sets of angles. Okay, so the angles are congruent between these two triangles, not necessarily the sides. Okay, and what we see is that we'll have triangles that are similar that will be different in size, but have the same basic shape. Okay, the angles which are equal are called corresponding angles. Okay, or corresponding vertices. And the sides that are joining those corresponding vertices are called corresponding sides. Okay, so note that corresponding angles will be equal to each other, their measures will be equal to each other, but the corresponding sides won't necessarily be equal to one another. Okay, and the symbol that we use to denote similarity between triangles is that. Okay, so a similarity statement is going to differ from a congruent statement by, we're still going to sort of write it out in the same way. We're going to make sure that the order of the vertices in this little expression, triangle ABC, we're going to make sure those vertices, the corresponding ones, are ordered correctly. Okay, so A will correspond to D, B will correspond to E, C will correspond to F. And we'll just put this little squiggle in the middle. I can't remember what that's actually called. Okay, and here is just a basic picture of what we can expect to see in this section. We'll have triangles that look like they have the same shape, but they might be different sizes. Okay, and the corresponding angles, like we have B and E marked out as congruent, right? And we could just sort of see, like looking at the shape, those are the two angles that have equal measure. Right? Similarly, angles A and D, based on this picture, appear to be equal, and the angle at vertex C and at F appear to be equal. Okay, so three pairs of equal angles, but the sides aren't necessarily equal. So how can we establish that two triangles are similar to one another? The theorem here is, it appears to be a little less stringent than those theorems that we saw in the previous section for congruence. Angle, angle. So if two triangles have two angles that are, or two pairs of angles that are equal, then we can establish that those two triangles are similar. Okay, so looking at this picture right here, these two triangles are similar because notice that angle A and angle Y are congruent, and angle B and angle Z are congruent. So question, why is this enough? Why do we only need two angles rather than three angles to establish that these two triangles are similar? Well, remember this sort of basic fact about the sum of the measures of the angles in any triangle. They're always going to add up to 180, right? So we know that angle A plus angle B, or sorry, let me write measure of angle A plus measure of angle B plus the measure of angle C is going to be equal to the sum of the, the angles in this triangle. So measure of angle, let me order this correctly, Y plus the measure of angle Z plus the measure of angle X. Okay, so what I'm going to do to sort of manipulate this equation here is it's given that the measure of angle A and angle Y are the same, and measure of angle B and angle Z are the same. So one way that we could do this is, okay, I'm not going to change anything on the left side of this equation. But I can substitute in for measure of angle Y. I can just write that as measure of angle A, right? Because I know that those two are the same numbers, so I can interchange them. This is just substitution. And I'm going to replace the measure of angle Z with the measure of angle B, because those are identical, so they're interchangeable. But measure of angle X, I'm going to leave that as is because it isn't really given here that X and C are equal to each other. That's what I'm trying to show. Okay, so now what I can do is I can just subtract the measure of angle A from both sides. I can subtract the measure of angle B from both sides. And all that's left is that the measure of angle C is equal to the measure of angle X. Okay, so I'll say therefore, angle C is congruent to angle X. Okay, therefore the two triangles are similar because we have 3 pairs of congruent angles between the two triangles. All right, so just a little informal proof right there of why the angle-angle theorem is sufficient. Okay, let's look at example 1. This is kind of a fun one. Are any of the angle or triangles contained in the figure below similar? If so, write out a similarity statement for each. And then here's our picture. Since we're trying to establish similarity, the angles within the triangles are more important than the sides here. So what angles do we have? I am seeing right angles. That's kind of jumping out at me. I see this right angle here. That is the angle GDE. And I see another right angle down here. That is GFD. So we have, right now I'm focusing on this big triangle here. This big triangle here, and then this smaller triangle, which I'll outline in blue. Okay, I hope that's helpful. I hope not too many people in the class are colorblind. They're like, okay, we got 2 gray triangles. All right, so the angles that we have that are congruent, we know that we have that right angle. We just need one more angle to be congruent, and then we can establish that they're similar. So do we see one more angle that is the same between these 2 triangles? Well, looking at angle G, I think we kind of got used to recognizing this in the previous section. Sometimes triangles, when they're drawn on top of each other, they'll have a shared angle. And look at this angle G right here, right? Or DGF, however you want to describe that. This angle is congruent to itself, right? So that gives us one more angle that is shared and that is congruent between these 2 triangles, okay? So I can say, I'll say since angle G is congruent to angle G, and we have that right angle, I'll say angle GDE is congruent to the angle, let's see, GFD. We know that these 2 triangles are similar, and, you know, again, like always, being careful about the order. I'll start with angle G, so triangle G, and then go to the right angle D, and then to the last one E, is similar, right? Not congruent, they appear to be different sizes, but it's similar to the triangle GFD. All right, so just using the angle theorem. Now, is that it? Is that all that we have? I am seeing one more triangle in here. I am seeing this triangle. Let's make this the green triangle. What about this one? Is this similar to either or both of those other triangles we were just talking about? Well, once we note that this is also a right angle, right? Because this is a line right here, right? GE is just a line. And that means that this angle, DFE, is going to be supplementary with GF, what is it, GFD. All right, so that means that that angle must also be 90 degrees, right? Because 90 plus 90 equals 180. Okay, and then now we just, we have the right angle, we just need one more congruent angle. And notice that the big triangle and this smallest triangle share this angle right here at E. Okay, so we have that shared angle, reflexive property. We can establish that the smaller triangle is also congruent to the big triangle. And then using transitivity, we can say that all three triangles are, sorry, did I say congruent? I meant similar. Okay, so I'll just make a little note here. So I'll say since angle, so the right angle, I'll call it EFD is equal to 90 degrees, which is equal to the measure of that big right angle. I'll call it angle EDG. And we also have that angle E is congruent to itself by the reflexive property. We know that this big triangle GDE is similar to that smallest triangle. Let me get the order of this correct. It will be DFE. Right? Yeah. Okay, so then the last thing, by the transitive property, of similarity, all three triangles are similar. GDE is similar to triangle GFD, which is similar to triangle DFE. Okay, and remember the transitive property, this is where, if A is equal to B and B is equal to C, then A is equal to C. Okay, so see how both the smaller triangles are both similar to the largest triangle, thus those two smaller triangles are also similar. Okay, so there it is. I'll put a box around this, just showing that these are the three similar triangles in the picture. Another proposition. The corresponding sides of two similar polygons are proportional. All right, and this is the really valuable thing that we get out of similarity. Okay, and we're going to be talking specifically about triangles in this piece here. But what are the corresponding sides if we're just looking at this example, these two triangles A, B, C, and D, E, F? Remember, the corresponding sides are the ones that are sort of between pairs of corresponding angles. So angle A and angle D seem to be corresponding, B and E seem to be corresponding. So the corresponding sides would be A, B, and D, E. Okay, what would be another pair of corresponding sides in these two triangles? BC, this is like the shortest side in each of the triangles, and EF. Those are also corresponding. Okay, and then the last, the longest sides of these two similar triangles, AC and DF. Okay, so when we say that corresponding sides of the two similar polygons are proportional, what that's saying is that we have these equalities. We have that, and I can color code this just so it's clear what's going on here. We have that AB, that side length, over DE. This quotient is going to be equal to BC divided by EF. And those are both going to be equal to this last quotient. You might be able to guess what it is. AC over DF. Okay, so if we take these proportions, they're all going to be equal. So this is what we mean when we say that corresponding sides of two similar polygons are proportional. Okay, and there are some other things that sort of pop out of this, like we'll also have that if we take the ratio of any two sides of one triangle, it's going to be equal to the ratio of the two corresponding sides in the other triangle. So like if we look at, for example, AB divided by BC, let me color code this. AB divided by BC. This is going to be equal to DE over EF. Okay, so these corresponding sides are not equal to each other. If they were, we would say that they're congruent. We would have that stronger sort of comparison between the two triangles. But in the case that we just have similarity, they won't be equal, but the sides will be proportional to one another. All right, so looking at this example 2, the two given figures shown are similar triangles. We want to find the length of the unknown side labeled with an X, and we want to round our result to the second decimal place if necessary. Okay, so here are two triangles, and we actually have measures for these side lengths, at least a couple of them in each triangle, and it's measured in terms of meters. Meters are our units here. So first triangle, we have the short side length is 4 meters and the longest is 12, and over here the longest is 15. And we are looking for X, okay, which is the measure of the shortest side length in the larger triangle. So we're going to use the proportionality. Okay, we know that, I'll say since the triangles are similar, I can set up the following proportion. I know that 4 over X, okay, so that's the ratio of these two short sides, should be equal to 12 over 15. That'll be the ratio of the two long sides. All right, and then I just want to solve this equation for that variable x. Now, how do I want to do that? I could, since I have x in the denominator, I don't like that. I don't like having my variable in the denominator, so I'll multiply both sides of the equation by x over 1. And that's helpful because on the left side of the equation, I'll get the cancellation. X divided by x is just 1. So then I get 4 is equal to 12 over 15 times x. And to get x by itself now, I'll want to divide both sides by 12, multiply both sides by 15. Or, a quick way to do that is just multiply both sides by the reciprocal of that. So I'll multiply both sides by 15 over 12. And since I'm multiplying by a fraction, I'll write this as 4 over 1. Just because with multiplication of fractions, we multiply straight across. So left side 15 times 4 gives me 60 over 12 is equal to, and then over here I'll just have x, right? Because we have 12 over 12, 15 over 15, so those all cancel out. Let's just make a big 1. So x is equal to 60 over 12. 60 over 12 actually simplifies. This is just 5. Okay, and we actually do have units here. So I'll say, or I guess it's written here that we have x meters. So yeah, x is equal to 5. I can just box that up. Okay, so just using proportionality of similar triangles to solve for x. Another way that we could have done this, so I was doing small side over the small side, big side over the big side, and set up my proportion that way. I also could have done it like this. I could have done 4 over 12 is equal to x over 15. Right, so rather than doing small side over small side, I did small triangle short side divided by small triangle long side, right? And then this over this. I would have gotten the same answer if I did it this way. Okay, so there is some flexibility in how you set up your equation for these problems. But there it is, x is 5. How about example 3? At 5 p.m., a 6-foot tall person casts a shadow 10 feet long. How long is the shadow cast by a 270-foot tall statue at the same time of day? All right, I'm going to draw a picture here for sure, and I'm hoping to see some similar triangles, right? Because I'm hoping to use proportionality to find the length of this shadow cast by the statue. So I'll start by drawing the person who's 6 feet tall, and I'll just do this drawing over here. So here's our person. And how about, let's say the sun is over here on the left side. So I'll just, there's our sun. Okay, and it's casting a shadow on this person, and here is the triangle that shows up. So, okay, the sun has this angle of elevation, it goes down like that, right? So the shadow that's going to be cast is going to be right there. Okay, and for the statue, the angle of elevation, which by the way is just this angle right here, the angle of elevation of the sun is assumed to be the same because this is happening at the same time of day. The statue is just much taller. So how about I draw the statue over here? It's going to be a big, beautiful statue made in the image of our little person over there. Okay, there they are. And we're going to assume that, this is just on level ground here. So now we get another triangle, which is definitely much larger, but are they similar? That's what we're hoping to find out here. So both of these triangles share this angle, right? This angle down here. So by the reflexive property, I know they have at least one angle in common. If I could find another angle, then I could use the angle-angle theorem to establish that these two triangles are congruent. So where is another angle that we could use here? Well, since we're assumed to be sort of standing on Earth here, and they're standing on this level ground here, the angle that this person's body makes with the ground is going to be 90 degrees. Okay, and the same is true over here. Right? These are both going to be 90-degree angles. Okay, so then we know, all of the angles are going to be equal to each other because they all add up to 180 degrees. So we have two similar triangles here. So, maybe I'll label these. Like sometimes I'll draw another picture where it's like, okay, here is sort of the simplified diagram. So there's the big triangle, and then we have a little triangle. I'll use a different color. The little triangle is down here. Okay. And sometimes I'll even label the sides. So, maybe I could call this, or rather angle the vertices. There's A, there's B, there's C, and then how about I call this vertex D and vertex E. All right, so based on this picture that I just came up with, I can say, so I'll say by the angle-angle theorem, I can see that triangle ABC is similar to triangle DBE. As always, making sure that I have my corresponding vertices listed in order. So vertex A corresponds to vertex D. That's why that comes first and that comes first, and so on. Okay, so all right, what am I trying to find again? How long is the shadow cast by the 270-foot tall statue? So let me write in these side lengths here that I have. I have that this is 270 feet, right? That's the height of the statue, and the person is 6 feet. And this short side length over here, EB, is 10 feet long. Remember, that was the length of the shadow cast by the person. And what we're looking for is this long side length from C to B. How about I label that with an X? And I want to find X because I was asked to find the length of the shadow cast by that statue. Okay, so let's find X. And to do that, I'll have to set up a proportion. There are a couple of different proportions that we can use here. How about I do... I'm going to try and set it up so that X is in the numerator. That just makes it a little bit easier to solve the proportion. So how about we do X over 270. All right, so that's the long leg of this blue triangle divided by the short leg of the blue triangle. And this will be equal to, again, long leg 10 of the smaller triangle over the short leg over 6. Okay, just double checking, making sure everything is set up correctly. I think that looks good. All right, so to get X by itself, I'll multiply both sides by 270. So I get that X is equal to 10 times 270 divided by 6, like that. And then I could simplify this. I could also just use my calculator. 270 times 10 divided by 6, I'm getting 450. All right, and our units here are feet, so maybe I'll finish up the problem by just saying the length of the shadow. So I'll say length of statue's shadow is 450 feet. And I'll box that up. Okay, so for pretty much everything in this first chapter, it's a very geometric chapter. It's a very geometric class all the way through. We're going to draw lots of pictures. We're going to draw lots of pictures of triangles. So when you're seeing a problem like this, if I don't see a picture drawn on your page, there's a very slim chance that you're going to get to the correct answer and set up the correct proportion. And if you do somehow have the correct answer and correct proportion, I'm going to be suspicious of how you did it. So drawing the picture is a really important part of showing your work for a problem like this. And as you'll all find out if you don't know this about me already, it's very important to me that you're showing your work. I'm known to withhold credit if I don't see work shown. So please draw clear pictures, and it'll help us all out in the end. Next up, we're going to check out some special right triangles, namely the 45, 45, 90 right triangle and the 30, 60, 90 right triangle. So both of these that we're going to focus on in the next couple pages are right triangles, meaning that one of the angles in the triangle is a 90-degree angle. All right, and that means that the other two angles, whatever they are in this picture here, we have, angle B and angle C. The sum of those two angles is going to be 90 because all three angles need to add up to 180. All right, so that's true for any right triangle, but we're going to focus on these special right triangles. The first one is 45, 45, 90, where these two smaller angles are congruent. And what this gives us is an isosceles right triangle. So remember, isosceles means that two of the side lengths are congruent in the triangle. So here's a picture of just our generic 45, 45, 90 triangle. Okay, and we like this triangle because the ratio between all of the sides is fixed. So down here is a theorem. If the right triangle is isosceles, that means that it's a 45, 45, 90 triangle. Then the sides are in the ratio x, x, x root 2. All right, so this is where the two small side lengths are the same, and that's x. And to obtain the length of the hypotenuse, the long side, based on the length of those short sides, just multiply the length of one of the short sides by the square root of 2. For any isosceles right triangle, the legs are x, and the hypotenuse is always x root 2. So a couple of examples of specific isosceles right triangles. Let me just draw one out here. And I'll do my best to make it actually look like a 45, 45, 90. Okay, that's not too bad. So here's our right angle. Those other two angles are 45 degrees. So one really common one that we use is if we have a hypotenuse of 1, then the lengths of the two sides are going to be root 2 over 2 and root 2 over 2. Okay, this might seem kind of random, why we're focusing on this particular triangle, but it turns out that in a little while, in the next chapter actually, when we're looking at the unit circle, our sine and cosine functions, a couple of important trigonometric functions, are going to be defined in terms of triangles that have a hypotenuse of length 1. Okay, but looking at this, like if we take one of the side lengths, so in this case right here, in this example, x is equal to root 2 over 2. Okay, so to get the hypotenuse, we would multiply this by root 2. Okay, so x times root 2 is going to be, all right, root 2 over 2 times root 2, and I'll write this as root 2 over 1. Okay, so then we get root 2 squared when we multiply, because remember we just multiply straight across. Right, root 2 squared. What is root 2 squared? Well, a second power and a square root, they essentially cancel each other out, and we just get 2 over 2, which equals 1. Okay, so this just sort of verifies that if this value right here is x, this value right here is x times the square root of 2. All right, so that's one common example, a particular 45, 45, 90. Another one that we use a lot, which I think is a little nicer in some situations. It's actually going to be a little bigger than that last one that we drew. So here's another 45, 45, 90. And in this example, the two legs are going to be length 1. Okay, so what happens if the two legs each have length 1? Well, to obtain the hypotenuse, we just multiply that length by root 2, so we get 1 times root 2, or just root 2. Okay, so in this example, we have that x is equal to 1, and then x root 2 is just 1 times root 2, or it's just root 2. Okay, and we could generate infinitely many 45, 45, 90 triangles. Just, decide what your side length, small side length is going to be, or the length of the leg is going to be, and then multiply by root 2 to get the length of the hypotenuse. Okay, so these proportions are going to hold for any 45, 45, 90. For example 4, we're asked to find the length of the missing sides of the given triangle. And looking at this triangle, it's, we've got a 45-degree angle there, so it's a right triangle. And we have these little congruence markers there showing that those two other angles are the same. This tells me that this is a 45, 45, 90 triangle. Okay, or I could call it an isosceles right triangle. All right, so given what we know about the proportions, we want to find the missing sides. So maybe I'll label each of these. How about I call this side y, and I'll call this side z. Doesn't matter what variables you choose for that, really. And but I'm choosing those specifically because I'm thinking of 9 root 2 as x. Right, where x is just the length of one of the side lengths. So over here I'll say, since this triangle ABC is a 45, 45, 90, I know that y is going to be equal to x, right? Because it's an isosceles right triangle. So y is going to be equal to 9 root 2. All right, so that's part of my answer already. I'll just write y equals 9 root 2. I'll put a box around that. Now, how about finding z? Well, z is going to be equal to x times the square root of 2. Just based on the proportions of 45, 45, 90 triangles. So that will be 9 root 2 times root 2. And now I want to simplify this. This is just 9 times root 2 squared. And whenever we're squaring a square root, those just cancel out. Sometimes I'll mark that out like this. The square root and the second power cancel out, and I get 9 times 2. So I'm getting 18 as the length of my hypotenuse. And I'll put a box around that. All right, so we have 9 root 2 right here and 18 as our hypotenuse. And that's all we wanted to do for example 4, just using those proportions to solve for those missing side lengths. Another one here, example 5, we have a square and we want to find the area. We want to find the area of the square. So recall from previous math classes, the area of a square is equal to the length times the width. Or really, this is true for any rectangle. In the case of a square, it's just like width times width, or in this case, s times s, or s squared. Okay, so really, as long as we can find s, then we'll be able to compute the area of this square. So let's find s. Okay, and this diagonal right here, okay, that diagonal is length 10. And what happens when you take a diagonal of a square? Well, it splits it into these 2 equal pieces, and it's going to bisect the angle at each of these vertices. So if these were originally 90 degree angles, and we're taking the diagonal, what we'll be left with is 45 degrees right here and 45 degrees right here. So we have 45, 45, 90 triangles where the hypotenuse is equal to 10 and the side lengths are s. So how can I set up an equation to try and solve for for s using the proportions we know for 45, 45, 90? Well, we know that 10, that side length 10, or the hypotenuse, is going to be equal to s times the square root of 2, right? That's how we get the length of the hypotenuse based on the side length. So I'll just solve for s in this equation, divide both sides by root 2. Okay, on the right side, root 2 over root 2 equals 1, so I'll just be left with s. And over here I'll have 10 over root 2, which is a little awkward. We don't like having radicals in the denominator. So I'll rationalize the denominator by multiplying by root 2 over root 2. Okay, this is a big 1. Right, root 2 divided by root 2 is 1. That's why we're allowed to introduce this factor without changing the value of s. So I'll have 10 root 2 divided by root 2 squared, which is just 2. And last step of the simplification, 10 divided by 2 is 5. So I'm getting that s is equal to 5 root 2. And okay, I don't want to get ahead of myself reaching for my rainbow ink. I'm not done yet. So this is part of it. First step is finding s. Now we can find the area. And we already have our formula. Area is equal to s squared. So that will be 5 root 2 squared. And sorry, I'm realizing my s's and my 5's look identical. But we know what we're talking about here. And we have to be careful when we are squaring something like this where we have more than one factor. We have to square both of them. So this will be 5 squared times root 2 squared. Just making sure that we remember our properties of exponents. This property of exponents kind of reminds me of the distributive property. You know, if there's multiplication here and we're raising to a power, we apply that exponent to each of the factors that are in the parentheses. So I get 25 times 2. So our area is going to be 50. And since we're talking about an area here, I will say units squared. All right, so just employing the ratios that we have for the side lengths of a 45, 45, 90, solving for that side length S and using it to find the area of the square. Moving on, 30, 60, 90 triangles. This is another special right triangle. For this right triangle, we have one right angle, of course, and then we have the other two angles as 30 degrees and 60 degrees. The triangle looks something like this. Okay, so this is not going to be an isosceles right triangle. This is a scalene right triangle, just meaning that all the side lengths are different. Okay, so there's our 90-degree angle. Over here is our 30-degree angle, and over here is our 60-degree angle. And here's what the theorem says about these. The ratios of the side lengths go like this: x, x root 3, and 2x. Okay, so I'll draw out the general triangle here. Okay, and yeah, the way that I remember this is the length of the hypotenuse is twice the length of the shortest side. And then the length of the other side, the long leg, I should say, you just multiply the short leg by the square root of 3. Let's see some examples here. One common example that we'll see, I guess we'll do the one that has a hypotenuse of length 1, because like I said before, right triangles with a hypotenuse of length 1 are very relevant to our definition of our trigonometric functions like sine, cosine, tangent, and so on. So let's look at this one. And maybe we could sort of generate these other side lengths. So if the hypotenuse is 1, remember the length of the short side is going to be, half of that hypotenuse. So this will be 1 over 2. And over here, the long side length is just going to be the short leg multiplied by root 3. So we'll get root 3 over 2. Okay, so this is actually the x equals 1/2 case. So that's one example of a 30, 60, 90 that we'll see a lot. And another one that is pretty common is actually going to be twice as big. Like always, I apologize that I can't draw very straight lines on Microsoft OneNote. I do my best. Bear with me. Okay, so this triangle, the short side length is going to be 1. So this is like the x equals 1 case. The hypotenuse will be length 2. And the long leg will have a length of root 3. Okay, so this is the x equals 1 case. Okay, so what we have here are 3 similar triangles, right? These are all similar. They have equal angle measures. However, they're not the same size, right? They're not congruent to each other. Okay, so I sort of think of these as like, this is sort of the one that's going to be relevant for trigonometry, right? That's like the trig 30, 60, 90 right triangle. And this one is also relevant for trigonometry, but this is like the sort of clean, nice side length version where we just have side lengths 1, 2, and root 3. Let's try an example. We want to find the missing side lengths for the given triangle. And we have a 90-degree angle, so this is a right triangle, and we're told that this angle is 60 degrees. So, by the fact that the sum of the interior angles of a triangle all add up to 180, this must be 30 degrees. So we have a 30, 60, 90 triangle. and we're given the long leg. That length is 12 units. And we want to find the short leg and the hypotenuse. So let's set up some equations. How about we set, first of all, how about we start by finding x? Let's find x. So how can we relate 12 and x in an equation using the proportions of a 30, 60, 90 triangle? Well, 12 is the long leg, so this is like the root 3. I always think of this as like the root 3 side. So if I take x and multiply it by root 3, I should be getting 12. So there's my equation. X times square root of 3 should be equal to 12. I'll solve this equation, divide both sides by root 3. So x is equal to 12 over root 3. I'll rationalize the denominator. And I get that x is equal to 12 root 3 over root 3 squared, which, as we know, just gives us not 2, 3. And I can simplify this down to 4 root 3. So there it is. There's the length of our short side. And I'm happy to have the length of the short side because once we have that, that's just x, then I can just double that to get the hypotenuse. So let's find the hypotenuse, which is now y. So over here, I'm going to find y. And I know that y is equal to 2 times x. So y will be equal to 2 times 4 root 3. Our hypotenuse is length 8 root 3. I'll box that up. Let's solve for the missing side lengths in this given triangle down here. And this time we have a right angle right here, and we're told that this is a 30-degree angle up here at this vertex. So then it's predetermined that this must be 60 degrees, right? And just to clarify why that is, like, you know, if we didn't know what this angle was, we could call it angle, you know, theta. How about? We know that 30 degrees plus theta plus 90 degrees would have to equal 180 degrees, right? Because the sum of the interior angles of any triangle is 180. So then theta plus 120 degrees would equal 180. Subtracting 120 from both sides, theta is equal to 60 degrees. Okay, so just to clarify what I mean when I say it's predetermined that this angle is 60 degrees, just by the constraint that the sum of the angles of any triangle add up to 180. Okay, now that we have that out of the way, we want to find P and Q, and we have that the hypotenuse is equal to 12 root 3. So I'm going to start with Q because it's the short side, right? The short side is like, we think of it as the x, right? And then we multiply by 2 to get this. We multiply by root 3 to get this. So I'll start with Q. And remember, the short side, or the shortest leg, is going to be half the length of the hypotenuse. So I'll just do that. I'll do Q is equal to, or I guess technically like the way that we set up the proportions before is like 2 times Q is equal to 12 root 3. And then divide both sides by 2. Q is equal to 12 root 3 over 2. So Q will be equal to 6 root 3. Okay, simple enough. So this is 6 root 3. And now we just want to find P. And P is going to be root 3 times Q. substituting in q, which is 6 root 3. So p is 6 times root 3 times root 3, or root 3 squared. So it'll be just 6 times 3. P is 18. All right, just another example of using those proportions, using similarity to solve for the side lengths of these special right triangles, 30, 60, 90s, and 45, 45, 90s. We're going to work with these triangles a lot in the next chapter, in the next few chapters, actually. So we will revisit this topic before too long, but this is just a brief introduction to kind of get us used to working with these. Before we move into section 1.4 on area and perimeter, working with some other geometric shapes, not just triangles, like rectangles, parallelograms, and so on. So I'll see you in the next video, section 1.4.